Some time ago, you could still find open spaces in the city where houses used to stand alone. But as predicted back then by Bob Dylan, the times they were changing. The Belgian population grew from 9 million in the early 60s to over 11 million nowadays. As Belgium maintained peace with its neighboring countries, no territorial expansion happened, leading to more and more houses and buildings that are built next to each other. This results in what we see today. Cities are fully built, and still there's an increasing demand for housing. When outdated buildings or houses do not meet the currently more severe requirements, two solutions are possible: demolition or renovation. Because of financial and environmental reasons, renovation is gaining importance. The current solution for this problem is a beam and block floor. Steel reinforced concrete beams are put in place between the walls, after which smaller concrete blocks are positioned in between. On top of this created formwork, another concrete layer of about 5 cm is cast. This system is suited for renovation, because it consists of smaller elements, but still, these elements are heavy. Concrete beams with a typical span of 5 meters have a mass of approximately 100 kilograms. Such heavy elements have a low maneuverability and slow down the installation process. At the Vrije Universiteit Brussel, we embraced this problem and turned it into a research question. Is it possible to design a floor which is lightweight in installation, but still contains the required structural properties? Therefore, we elaborated the idea of combining concrete, carbon polymer composites, and cement composites. To solve this question, I first made a theoretical approach to predict the floor's structural properties. All equations and formulas are integrated into MATLAB. Standard formulas are developed for traditional steel concrete cross-sections. Composite concrete cross-sections, however, have irregular shapes and different material properties. Therefore, an analytical calculation program is built so that all structural properties of any arbitrary cross-section with any material can be calculated. Different techniques and philosophies are merged into one analytical model. First of all, the non-linear material behavior of concrete and cement composites is modeled as accurate as possible. Second, due to the unusual and irregular shape of this new cross-section, a discretized fiber model is built, resulting in small discretized elements that are treated separately in the calculation. Third, on this discretized cross-section, structural mechanical formulas are applied. These formulas result in small forces per discretized element, on its turn resulting in the global bending capacity of the cross-section. Fourth, to speed up this heavy calculation, a smart search algorithm that refines its strain step is integrated in a model to obtain an accurate strain profile within a limited amount of time. Finally, together with the design philosophy and guidelines from Eurocode 2, the analytical model was built to predict the structural behavior. Besides this theoretical study, we also investigated its behavior in practice. Therefore, an extended test program with 28 flexural beams was carried out. Local strains were measured by strain gauges at the most crucial positions, such as the middle of the span. To have an idea about the strains all over the surface, digital image correlation is used as a full field technique. By the means of small black dots on a white background, the displacement is measured all over the surface by two cameras. To identify problems at the inside, not visible from the outside, acoustic emission is used. Acoustic sensors listen to the waves that are emitted by the cracking of the elements. Finally, the deflection is measured at different positions underneath the structure. This is done through several LVDTs. Equipped with all these techniques, these 3-meter span beams are loaded until failure. What are the results of this extended test program? First of all, we check the validity of the Euler-Bernoulli assumption through the DIC analysis of the beam side. All cross-sections remain plane, and thus our assumption is correct. Identical beams exhibit almost the same stiffness behavior, which is a nice result considering the manual production of these beams. Adding the theoretical prediction to this graph, we notice that also the stiffness is well predicted, but there's a large overshoot in the failure load. Considering strength and stiffness, this hybrid reference beam with comparable dimensions but lower mass shows to be a viable alternative for reinforced concrete beams with a span of 3 meters. The presence of carbon strips strongly influences the stiffness, and therefore carbon strips are needed in the design to fulfill all deflection requirements. To increase its fire resistance and decrease its environmental impact, experiments have shown that the carbon strips cannot be replaced by unidirectional glass fibers, but by unidirectional carbon fibers. Also, the theoretical prediction is in agreement with the experienced stiffness, but exceeds again the experimental failure load. This made us thinking again. This large overshoot was due to the occurrence of shear failure phenomena, so I decided to investigate this shear behavior more into detail. Again, first a theoretical study was performed by returning to the fundamental formulas of the different phenomena that contribute to the shear resistance: the uncracked concrete, aggregate interlock, and double action. Similar to the previous large span experiments, 10 short span beam tests are performed to verify this theory. Good correspondence is found on the level of the concrete. However, further research will need to focus on the contribution of the composite box. So we obtained very nice results on the tested beams. But what if we extend our study to floors? Statical tests are performed on 4 floors, ending up with the same results. The hybrid floors have a sufficient load-bearing capacity and the stiffness is well predicted. To show its fire resistance, one floor with a span of 4.2 meters is subjected to a fire. The good fire resistance of the different composites was proven by the fact that the floor only collapsed after 40 minutes. At this stage, we have a lightweight concept that can save up to 89% on all installation elements of the beam and block floor. Moreover, we have a theoretical calculation tool and an extended experimental validation. However, cost may still be an issue to enter the market. To close the gap between this research and the market, a multi-objective optimization tool is built which allows the user to choose between solutions which are lightweight but more expensive, or rather solutions which are cheaper but more heavy to install. The advantage of this lightweight in installation floor system can best be summarized by a small movie that shows the ease of handling of these big lightweight elements. An analytical model is built to predict the bending behavior, and a first attempt is made in calculating the shear resistance. To validate all these calculations, 38 beam and 5 floor tests are carried out. Finally, a multi-objective optimization is elaborated to show the trade-off between mass and cost that can be made by the user. In this way, this thesis provides an answer to a practical 2-day problem by the combination of theoretical research and an extended experimental validation.